Hello. So let's talk about science and let's talk about research and especially fundamental research today. So who has never been fascinated by this type of collective movement? If you look at this call of fish, it looks like a single individual. It looks like a conductor of an orchestra is directed them. It looks like a superorganism, and we are always fascinated by this type of behavior. These behaviors are quite common because we can observe them in starling. You've seen that in Toulouse, this flock of birds, sometimes they're billions, and they seem so highly coordinated. It's a very complex task to really coordinate with all your neighbors in the flock. But this is not the most complex task, because in this type of behavior, the group is going from a point A to a point B. So they're going in the same direction. There's different type of collective behaviors that are more difficult to understand, is what we call the bidirectional flow. And there's two major examples, ants and us, humans. We have to deal with this problem every day. So if you move all in the same direction, it's quite simple. You need to adjust your movement to your neighbors around you, but it's a simple thing. But imagine now you have people in front of you. You need to avoid them because bumping into each other can be really painful. So there's a theory in traffic, and to reassure you, is the only equation you will see in this talk. So there's a very particular equation in traffic theory that a lot of engineers are looking at, is the flow equal density multiplies speed. So the flow, it's simple. It's a number of individuals crossing a surface per unit of time. The density is the number of individuals in this particular surface. And the speed is the time required to cross this surface. So three simple variables. So now, we are looking at the link between these variables. Something we notice is that when you increase density, so for example, you go from 1 pedestrian per meter square to 8 per meter square. So here in this room, I guess you're very kind of low density, but it looks like more 1 to 2 person per meter square. If you increase this density, your speed, if you're moving, is gonna decrease. Why is that? Because you're going to bump into each other. And so you need to avoid, and each time you try to avoid somebody, you are losing time. And when density increases, the number of collisions increase. And so now, what's going to happen to the flow if the speed decreases when density increases? The flow looks like that. So at low density, you have a very small flow. More you increase the density, more the flow increases. And you reach a maximum. So you have to know that in pedestrian, the maximum is 2.5 pedestrian per meter square. If you go up this density, the flow decreases. And you get completely stuck if you're 8, even with 6 people per meter square. So to illustrate that, I have these little videos. So this is 1 person per meter square, just to give you an idea of what is represented in terms of density. So here it's 1.5, 2 person, you still start to be crowded. Already we are the flow is decreasing, and we are getting stuck. So the highest density in Europe, we can reach 9 to 10 person. In Asia is a bit larger. People can reach sometimes 11 person per meter square. Just imagine 11 person per meter square. So why coming to ants when you study traffic? There's lots of reasons, and I'm going to give you a few reasons. First, they're very popular. They're popular among kids. Kids love ants. They have been the subject of lots of movies for kids. But it's not only kids. Adults love them too, but it's more like the subject of horror movies. They look scary sometimes because there are billions of ants moving together. They are also very popular in advertisement because ants, people think that they're very hard worker. They work together, they're very cooperative. So usually people always think that they come up with this smart solution. So in this video, for example, you can see an ant directing the other ants to do kind of a trap for these very weird animals. And they find a solution. Is that true? Is that ant so smart? So I'm going to give you first some generalities about ants because there's lots of urban legend about ants. So first, something very weird, ants are called eusocial, not social. We are social, they're eusocial. Eusocial means you super social, you more than social. So it's the same for bees, naked mole rats, these weird animals living in South of Africa. I'm sure you've never seen this one. They live underground. And termites and wasps. What does that mean being eusocial? They have a queen. All these animals have a queen. So what is queen doing? In fact, it's the only individual reproducing inside the colony. So imagine in this room if only one person was allowed to reproduce. So this queen is laying eggs all day. That's her job. She's laying eggs, laying eggs, laying eggs. These eggs become adults, but sterile. These adults, they cannot reproduce. And they call the workers. So the workers, they can do very different things inside the colony. For example, they can be nurses. They take care of their little sisters, the babies. Yeah, because in ants, most ants are girls. There are very few male just during the time of reproduction, and they just died after the mating. So no male in a colony usually. And the workers can be also reserves. Reserves are like little fridge. So they carry the food inside their belly and they share it with every member of the colony. They can also be architects, like they are building the nest, the one who are digging the galleries. The one you know better are the soldiers, the one who sting you when you touch them. So this one defends the colony. And they are girls too. And the most interesting for me are the foragers. It's the ants that go outside to collect food for the whole colony. So these ants represent almost 10% of the colony. So you have to know that when you see ants in your kitchen, they are the foragers. So if you see foragers in your colony, you have to imagine that 90% of the colony is hiding somewhere else. So you just see 10% of the ants. These foragers have a very particular way to communicate with each other. When they move around, they lay a chemical trail, like the story of Little Tom Thumb with these pebbles, exactly the same way. So they move and they lay this chemical trail, and this chemical trail is very important because it helps them to orient in the space, to find the nest and the food, but it also attracts lots of other ants. And the other ants, they're going to follow the trail and they're going to reinforce it. So after you have a very, very dense trail. So you've seen a trail once in your life, usually in your kitchen, but perhaps you've seen them also in the field. They can be very large and very long, sometimes up to kilometers for example, in army ants in Africa. So it's really good, this system, laying a trail, because you attract your congeners directly to the food source and you can't get lost. But sometimes you could attract too many ants. And perhaps you could have to deal with problem of traffic jam. And also, if you recruit too many people to the food and you just have a little cookies and you are 1 billion there, there's going to be crowding at the food source. So ants have to deal with this problem of crowding on a daily basis. So it's where I come to study traffic jam in ants. I was wondering how ants regulate the problem of traffic, because we are not doing that so well. So I was wondering if they have solutions. So what you need to do when you want to study this problem, you need to observe ants. And this can take hours. And sometimes it can be very boring just watching trail. But you have to do it. So we came up with a very simple experiment. So you have a nest connected to a food source by a bridge. This bridge can be wide, and this is our low density condition. Or the width can be narrow, and it's our high density condition. So we played with width like that for hours and looking at how ants deal with the problem of density. So now I'm going to show you the relationship I show you for pedestrian, how it looks like in ants. Is that the same? First, the relationship between density and speed. As you can see, as pedestrian, the speed is decreasing with density, but you can see that it stabilizes at one point. It's like they don't go to zero like us. They don't get stuck. What's happening with the collision? So the same. When you increase density, of course, the number of collisions between ants increases too, but it stabilizes also. That's very weird. You increase density and suddenly collisions are not increasing anymore. So what is going to happen with the flow then? This is how it looks like. So when you increase density, the flow reaches a maximum, but this maximum stays. So I've been studying traffic jam, but I'm not studying traffic jam, in fact, because I've been studying ants for 10 years, more than 10 years, and I've never observed once a traffic jam in ants. I'm still looking. So just to give you a comparison, when humans were getting stuck, it was around 6% per meter square. And in ants, they're still going, and there's more than 25 ants per centimeter square. These represent like we would be 11 in a meter square, and they're still moving. So they're very efficient. So the question is, how they do that? Very simple solution. They have priority rules. So in ants, they have lots of different rules when you go on traffic. So first, we imagine a situation, you have an ant facing a group of ants, 5 ants. So she has two solutions. She can try to bump into them, or she can try to avoid them. So in this type of situation, the ants would move away. And it would always be her moving away and not the group. So in fact, the decision is simple in ants. They look around. If they have no space, they move forward. If they can move on the side, they move on the side. It's very simple. They respond to just local rules. The second rule that is very funny is like when an ant is carrying food, it's always given the way. So you would think, oh my gosh, ants are very polite. They let pass the ants that carrying food. It's not like that. If you look at this picture and you see an ant carrying a load, they are like that and more like that. And it's quite difficult to move. And in fact, these ants are just not moving. They go forward like that, and the other one have to avoid. So it's not a very politeness. It's like, I want to go to the quickest way, and the quickest is to go around these ants carrying a big load. And so like that, there's lots of different priority rules that they can change according to condition. So it's exactly the opposite. Our traffic rules are always the same. In ants, they change. It depends. It's automatic. It's look like at the situation. So they have a very different way of organizing themselves. We always thought, most of the people thought that queen is like giving orders to the other ants, should do that, should do that. But the queen has no idea. But she has no idea that some ants are going outside to collect food, so she cannot regulate traffic. So we have this kind of way because we humans, we work like that. We have a boss giving orders, usually, not all the time. But they work in a very different way. Ants, it's what we call self-organized. They react to the local rule and interaction to their neighbors. So they're going to adapt their response according to the ants next, not the ants with 10 meters away. So it's a very efficient way. It's more like an anarchist society. So it's a very interesting because usually ants, if you take it individually, they're kind of dumb. They're not very smart animals when they're alone. But as a group, they can do very, very smart things. So they can build rafts, for example. They can build bridges. They can have a smooth traffic. They can also build very complex nests. So for example, ants can have like giant nests where each room have a different temperature and different level of humidity. They can do that just by manipulating the wind. And they do that with very simple rules. So of course, ants became a big source of inspiration, especially in robotics, because ants in a colony are very disposable. If you kill one ant in a colony, the colony won't stop functioning. It will go like nothing happened. And if you think like that with little robots, sometimes it could be better to have very small, cheap robots who, as a collective, are very smart than a one unique, very expensive and very complex robot. So depending on the situation, sometimes like working like an ant could be a very efficient way. Ants also have been inspiration for lots of engineers, and especially in telecommunication or in your mobile phone, for example. There's what we call ant algorithm. Ant algorithms are like small equations who are like dealing with very complex problems. So we can imagine when you want to sell cloth, like Catherine, for example, and she has a problem, she needs to link lots of different cities in France. Like we can imagine 15 cities. This problem, to find the shortest way to link these 15 cities would take you ages because you have to take all the possibilities. With an ant algorithm, it takes 3 seconds. So this optimization problem has been used a lot for the salesman problem, for example. And perhaps something more familiar to you, an airline company has been using ant algorithm, is the airline Southwest. They have been using ant algorithm for pilot when they arrive at the gate. So the gate is attributed to each pilot using an ant algorithm, and they have less problem than all other companies. So what I wanted to do with this talk is show you that some organism who seems so different than us can inspire us. And sometimes we have to stop and look around and respect these other organisms. We're not the smartest species. These species can teach us solutions that we would never have imagined. It's just a different way of being organized. I don't say that you could use ant algorithm for everything, but for some problems, especially crowd problem, traffic problem, when there's lots of different individuals you need to regulate at the same time, ant algorithm could be the most efficient way. So I think we should sometimes invest more in fundamental research, because if you say you work on ants, people will say, oh my gosh, we're paying you to do that, to play with ants all day. But sometimes we can give solution. So the message today would be like, invest in fundamental research. Thank you very much.
Merci beaucoup, Audrey.